All right, ladies and gentlemen, here's a quick video of review for the Unit 20, the wave unit for you guys. I've got the test here in front of me, and I'm going to kind of go through it at the same time as I go through the notes, making sure I'm hitting everything that is going to be on that test. Again, there are plenty of review questions that you should be squared away on, but this is just a little something extra to sort of guide you as you're getting ready for this test. So waves, traveling disturbances, carrying energy. We've got mechanical waves. They have to travel through matter. Examples, earthquake, sound, water. Waves on a stringed instrument. And electromagnetic waves. Those are those light waves that can move through a vacuum. Number one, the difference between transverse and longitudinal waves. You need to know that transverse waves move perpendicular to the motion of the particles move perpendicular to the motion of the wave. So if the wave moves that way, the particles move up and down. So we would have this particle that is oscillating back and forth like when you crack a whip. Also be able to label the wavelength like this. We've got the amplitude there, and then we've got troughs, trough, and we've also got crests up top. So be able to label and describe what a transverse wave is versus a longitudinal wave. In this case, we are moving our motion parallel to the wave. The particles are moving in the same direction as the wave. So again, we've got a wavelength here from a compression, which is one of these areas, to a rarefaction, which is one of these stretched out areas, kind of just like the trough and the crest. The amplitude is actually how crunched up it gets or how spread out it gets. You won't really be asked to label that on a test. From there, we moved on to using this equation. It's the first one you're going to need for the test. They will not be given to you. You need to have that down. So we talked about speed of a wave, that's the S, equals the distance it travels per unit of time. And that all depends on what type of wave it is and what medium it is moving through. I'll have some other stuff as we go comparing sound versus light. But depending on the medium, that can change the speed, and depending on the type of wave that can change the speed as well. Make sure you know how to use those equations, and also be able to do what we call the echo problems. Remember that this is just straight up, you would take the 340 equals 5 divided by t and solve for the time. But over here, for this next one, we've got an echo problem. Remember, you're going to either need to multiply by 2, because for this, if you hear the echo, you're either talking about twice the distance. If I give you the distance, you need to double it because the sound has to go there and back. Or you need to take this time and divide it by 2 because I'm asking about just how far away something is, and I'm giving you the time it takes for it to get there and back. So be aware of that. Double check some of the answer keys for the homework to make sure you're doing those correct. Light can do that as well. We can use the exact same equations, still using distance and time. Make sure your meters and seconds for your units, not using minutes or hours. Make sure you convert those into the proper units. There's another example of the compressions and rarefactions here that I kind of skimmed over earlier. Here's a little bit clearer design of that. Here's an echo problem. Kind of again, I think whatever problem it was said that the sound took 1.5 seconds to get back, so we divided that by 2 because that would be just the time to get there, and then use that with the speed of sound to get what we were looking at. Same with this submarine problem, I think was on homework worksheet number 1. The next equation we've got is up here. The speed of a wave is equal to its wavelength times the frequency. Your wavelength is in units of meters. Your frequency is in units of hertz. Frequency is something per second. Hertz is the same thing as a per second as your unit. So make sure you know how to use this equation. Just being able to plug in the numbers and calculate there is, I'm looking just here at the beginning at about 3-ish questions are just straight up that. So that's about 11-ish, an 11th, so like 9% of the test is just being able to do that. The other thing to realize, and it'll come in more as we go, if you lower the wavelength, you end up with a bigger frequency if you're keeping the speed the same. So large frequencies result in low wavelengths. We'll apply that a lot as we get into the light and sound pieces of the test. So keep that in mind. A couple examples here. Frequency, if you change the speed, a bigger speed with the same frequency gets you a bigger wavelength. That was a lab we did, so you don't need to worry about that. This idea of interference, if you have what's called constructive interference, that's when your waves are adding together, and that is when a peak meets a peak or a trough meets a trough. So if a problem says that you're being, two waves pass and they're both either peaks or troughs, you add their amplitudes together. So let's say that this guy was 5 and this guy was 3. This resulting wave here would be 8. On the other hand, destructive, you subtract them, those peaks. A peak is meaning a trough. So if that occurs, let's say this guy again was 5 and this was 3, you would take 5 minus 3, and that would leave you with an amplitude of 2 for your final wave. Little target quiz, maybe take a look at that. A little bit more about interference, a little bit cleaner notes here. When these waves pass over, they don't actually change the individual wave at all. They just interfere at that point and then sort of keep on moving. Constructive, again, versus, it's supposed to say destructive. Destructive. Interference, couple of notes there, but it's the same thing as we just talked about. One of the big things here is that if you've got two sources of waves, so let's say we've got two different speakers or light coming through two slits in that double slit experiment that we talked a little bit about, if your observer is closer to one source of the waves by a whole number of wavelengths, so let's say I was 7 wavelengths away from one speaker and 8 wavelengths away from the other, or if I was 14.5 and 13.5 wavelengths away, or 9.8 and 10.8. As long as it's a whole number, it could be 9.8 and 13.8. As long as that's the case, my interference is constructive. But if I am a half wavelength, so 0.5 closer to one than the other, or 1.5 closer than the other, 2.5, 3.5, whatever that occurs, I end up with destructive interference. Those waves will come out of what's called out of phase. So that would say, let's say if I had one wavelength from one, but I only had half a wavelength from the other, when those two hit, I've got one peak and one trough, resulting in destructive interference. The principle of superposition basically says that whenever two waves pass over, whenever we get that interference, each place on that wave adds up with whatever place it is overlapping with. So you can get different shapes that when they add up, you can get these two. So let's say this guy was moving this way and this guy was moving that way. When they overlap, I would end up with a shape that looked something like that. So take a couple looks. I know there's multiple questions in the packet about this idea of superposition. Look for the ones that are just, here's this wave, when they collide, what does it look like? When it's the two peaks, when it's that constructive, one just gets stacked on top of the other. When it's destructive, so like here, when it's like that, you actually end up taking sort of a slice out of that one. So on this side, because my amplitude was 0 downwards, I end up with that whole bit still being there, but then I progressively lose more and more as I move to the left. So take some time with those, get used to different shapes that you might see. Could be circles, squares, triangles, but it will be a question or two that are just like that. Moving on to the idea of reflection, this is when you have any wave hitting a surface and it turns back, that is reflection. And we say that the law of reflection states that whenever light hits a surface, we call that the angle that it hits the surface, the angle of incidence, and that angle has to be equal to the angle at which that ray or that wave reflects off and bounces off. And the angle that we're talking about is always measured from a perpendicular line to the surface that we're talking about, and we call that a normal line. So a couple things to be able to do, be able to draw a diagram if I give you a shape, be able to draw its reflection in a plane mirror, things to notice. Make sure that the distances for each part of it are the same distance away. So that the top of the T is 1 meter. For the object, it's also got to be 1 meter for the image, and sort of match that up, and be able to draw rays. So kind of down here, whenever we have a angle here, make sure that the angle out is equal to the angle in the normal line that we're talking about. Would be just like this, perpendicular to the surface of my mirror, so that this angle equals this angle right there. And shown again here, the red line is the normal line, that's my surface. I bounce off the surface, this angle must equal that angle. That is my law of reflection. Also be able to draw, if I give you a curved mirror, realize that it's still got to be a normal line to the surface at that point. So it will appear as if you're coming in straight and then being reflected at an angle, but that is because the normal line is off at an angle. So we actually still do get the same angle on both of those if you look there. So be able to draw that concave versus convex. Remember, the concave all comes into one point. The convex all shoots out to different points, but if you were to trace those down through, they would actually intersect over here, sort of inside the mirror for you. We also have refraction. Refraction is what causes, if you have something in water and you look at it, it looks like it's broken or bent. Whenever light travels into a new medium, it changes speed. When that occurs, the light appears to be bent. We actually bend it a little bit. And this is our third equation out of 4. What we call the index of refraction is equal to the speed of light divided by the speed of light in whatever you're talking about, right? Whatever medium you're worried about the index of refraction. This C is 3 times 10 to the 8th. That is the speed of light for a vacuum, and the V is the speed of light in the new medium. Bigger indexes of refraction means slower light moving. N is always bigger than or equal to 1 because the speed of light in a vacuum gets a index of refraction of 1. So if I give you the speed of light, you'll always know 3 times 10 to the 8th. That number will be given to you. So if I give you the index of refraction, you need to be able to determine the speed of light in that material that we're talking about. Just plug it into the equation and solve for it. And again, this refraction only happens when we are changing speed of light, right? We're not just all of a sudden bending light all over the place. We only get it when we change speeds, when we change mediums. So if you're going from a faster to a slower medium, you bend the light towards the normal line. So if you draw your normal line, you get that. Apologize if you heard that noise. That was actually my ringtone. My insurance agent was calling me so I could get new car insurance and save a little money. But back to this. If you slow down, you bend towards that normal line, and vice versa. If you speed up, you bend away from that normal line. So instead of being here, if I sped up, I would bend like that and probably go through there. So moving on, line bends away to the normal, speed is faster. So if I go from water to air, I bend away from that normal line. A lot of junk here. Same sort of stuff. Couple little calculations here showing that speed of light indexes of refraction. The higher your index of refraction, that means the slower your speed of light is through that medium. The 3.8, that, or I'm sorry, the 3 times 10 to the 8th, people refer to as the speed of light, but that is the speed of light through a vacuum, which is not the same. Same notes kind of again here. Did those. All right, and last one, and last sort of property of waves, and these are true of all waves, the interference, the refraction, the diffraction, all of those all waves exhibit. They're not exclusive. Some of them are easier to talk about with light or sound, but all of them do it. It is a property of waves, not a property of one type of wave. And the last one is if we go through a slit, hole, or other sort of barrier, we get what's called diffraction. So a couple main points about diffraction. Number one, this is what allows you to hear around corners, the fact that we get sort of this pattern here. So as light goes through a hole, say like that, the hole becomes a new source of the wave. So instead of just going through and having this little thin bit, instead you actually get a full wave coming out through. What's being shown up here is what's known as the double slit experiment or double slit interference pattern. When you shine a light through two separate slits, you get these two waves, so you get diffraction. But then when those waves hit a screen on the other side, if you want to call it that, sort of a sheet, you get these patterns of being bright and dim and bright and dim. That's because those two waves are then interfering with each other, which is interference. So the double slit actually has diffraction as well as interference aspects to it. Over here we've got this as our bigger idea here. The bigger the wavelength, the more it diffracts. So bigger wavelengths end up diffracting more than smaller wavelengths. That's why you can hear around a corner. Waves, sound waves tend to have rather large wavelengths on the order of a meter or two, whereas light is a very small wavelength. We're talking about nanometers for visible light, and it's because of that you can't see around a corner, right? We're not bending those light waves into doorways or out of doorways. They tend to go more straight because they have smaller wavelengths. Another thing you can do to affect the amount of diffraction you get is actually make a smaller opening, or what we call an aperture. By doing that, you can get more diffraction. The smaller the opening, the more diffraction, and the better chance at diffraction you have. So again, any type of wave can diffract, any type of wave can refract, any type of wave can interfere with other waves of the same type. But for diffraction, bigger wavelength means more diffraction. That also means that lower frequencies get more diffraction because, like we talked about earlier, if you lower the frequency, you are increasing the wavelength as long as the speed of that wave is staying the same. Click through some more stuff here. And the last thing we've got, not really the last thing yet, is Snell's law. There will only be one problem about this on the test. Be able to use this equation. I will give you 3 of those variables. You plug in for the third one. I give you 3 variables. You solve for the fourth. It'll just be sort of an algebra problem. Make sure that your calculator is in degree mode when you do that. But basically, Snell's law says that the bigger the difference in the indexes of refraction, the bigger the change in angle, the bigger that shifting of refraction, we're back to refraction with Snell's law, the bigger that appears to be. We did a little mid-unit review. Here's a couple more diagrams for you, the transverse and longitudinal waves drawn out for you. Problem with yodeling. Couple of things here. Here's some more examples of that, the superposition stuff. If these two added together, you would get this shape, but if these two added together, you would get that shape there. Remember, we're always talking about the angle with the normal line being equal, not necessarily the angles with the surface. Diffraction. These are the 4 equations that you need. Those are the only 4 equations. This number will be given to you, so don't worry about that. Then we kind of started our second half of the unit. I know it says AP, but I just adapted it for you guys. Differences in frequency for sound. We just sort of split the rest of the unit into sound versus light, sort of the differences there. Differences in frequency, we perceive as differences in what is known as pitch. So this is the highness or lowness of a sound, if it's high pitched or low pitched. And again, just like we just said, the lower the frequency, the bigger the wavelength. So it might ask which has a lower pitch, but give you wavelengths instead of frequencies. Big wavelength means low frequency. Moving on from there, sorry, I was adjusting something. Below the human range of hearing over here, 20 to 2,000 hertz. I'm sorry, 20 to 20,000 hertz. Below that is known as infrasonic. Above that is ultrasonic, like an ultrasound. Loudness is all about the amplitude. Bigger amplitudes result in louder sounds. We don't perceive it linearly. If you double the energy, you don't actually double the loudness. Instead, we have the decibel scale, which you don't have to do any math with. But we also talked a little bit about resonance and this idea of sounds being able to, or waves being able to sort of hold a steady shape on an object or in a tube. And this is known as resonance. Let me just go back and double check, make sure I didn't miss something important here I thought I had. It might be later on. Not there. I think I'd do it later. Okay. Things you'll need to know with the sound stuff that we talked about. We did musical instrument day. I will ask one question that has to do with one of these harmonics of either a string or an open-ended tube or a closed-ended tube. You need to be able to, it will come from one of those 6. So first or second for a string, first or second for the others. Make sure you can both draw these and label the nodes and the antinodes for each one. And a little sort of hint, if you know the first harmonic, all you have to do is add on another loop to it, regardless of which type of wave you're talking about. It's always just about adding a loop. So I start with one of these loops with nodes at the ends. For the first harmonic on a string, I add a loop to the end and sort of smush it together. So then I get these 2 antinodes with the 3 nodes. For an open-ended tube, same thing. This time I just end with antinodes and have a node in the middle. But then if you see here in the middle, I just sort of spliced a whole loop right into the middle there and relabeled it. And then for closed-ended tube, I put a loop right here at the beginning. Has a node at the closed end and an antinode at the open end. That is actually known as the third harmonic, not the second harmonic, so just be aware of that. A little bit of that, a little bit of that. And I guess I'm missing a slight note. Let me go look for it real quick. So one of the other things about sound, last thing here about sound, is the sort of rate at which it moves through different types of substances. Sound actually moves fastest through a solid because it is a mechanical wave, and for air it is, or I'm sorry, for sound it's also a longitudinal wave, but mostly because of the fact that it is a, a mechanical wave. The more tightly compact the stuff it's got to move through is, the faster it can move. So a solid moves fastest through, then a liquid, then a gas. Remember that a sound wave cannot travel in a vacuum because there's no stuff for it to move. To get sound, you actually have to have stuff vibrating back and forth. That is different than for light, or what we call EM radiation, electromagnetic radiation. That's just light. So that whole spectrum we talked about, all represented there as either light or the electromagnetic radiation. Let's take. Light is caused whenever you accelerate a charged particle. So that could be either speeding up, slowing down, or changing direction. A proton or a electron or some sort of ion, something with a charged particle on it. So if something is an ion, that is also with a charge. So keep that in mind. Light travels fastest in a vacuum. That's that 3 times 10 to the 8th value. It slows down a little bit when it goes into a gas like air. It slows down more when it goes into a liquid, and it slows down more when it goes to the solid. Now that is, usually true. There are some exceptions, some like sort of wash over there, some liquids that slow it down more than solids, but as a general rule, that is the case. You can sort of take that pretty well there. Last thing with light, really, and I know we talked a lot more in depth, be able to rank these, I should say, not necessarily rate, but rank them. If you go this way on the spectrum, you are increasing your wavelength, so bigger wavelengths are down here, but smaller frequencies are also down here. Bigger frequencies, smaller wavelengths. With light, energy is associated with frequency, so these gamma, X, and UV rays have higher energies, whereas radio waves are not very energetic at all. We can only see in this little section right here, Roy G. Biv, again, wavelength getting bigger as we go to the right, and frequency getting bigger as we go to the left. So anything that is to the right of this visible light are waves that are too long for us to see. Anything that is to the left is too short for us to see. So really being able to rank those is your biggest thing, and realizing where stuff is bigger or smaller than we could see. Because we just fit right in there. You don't have to be able to divide into FM, AM, and long radio waves. Just recognize this as radio waves sort of as a whole. And certainly don't worry about any of those numbers. Don't worry about where those lines fall. Just know the order. Talked about each individual one. And last but not least is the Doppler effect. So if you are moving towards a source of waves, the frequency that you perceive increases. So if you're moving towards a source of sound, that means that you get a slight shift upward in frequency. And if you're moving away from it, it is a shift down in frequency. And the frequency shift we're talking about is small. We're talking about a couple of hertz. We're not talking, doubling or halving the frequency. It's a little bit. The same is true with light. If I am moving towards a source of light, it shifts upwards in frequency, so it might shift from green to blue. Or red to orange. And if I shift downwards, if I'm moving away from something, it would shift my frequency down. So I might go from ultraviolet down to violet, or I might go from red to infrared. So keep that in mind for both of those. It applies to both light and sound. It applies to all waves. All waves can be have interference, refraction, diffraction, the Doppler effect. They're all general stuff with waves. Differences between types of waves would be the speed at which they move, and really whether they're transverse or longitudinal, whether they are mechanical or electromagnetic. And that's kind of it. Waves, you can really talk about a lot of it in general. You don't have to worry too much about specifics for different types. A lot of the rules apply to both. I hope this is helpful for anybody who chooses to watch and listen. We'll do some review in class tomorrow. Some stuff that wasn't necessarily on the review packet that we added on to the test. So we will cross that bridge when we come to it. Have a good one, everybody.